Hello and welcome back to Chapter 16, where we're covering the atmosphere. The next topic is to talk about radiation at or near the Earth's surface and what kinds of radiation do we receive, how does it behave, and then how is it distributed over the Earth, and what are some of the variables that affect the distribution of radiation over the Earth's surface. We will step back and look at that in more detail in the final section as it relates to the materials on the Earth's surface. So the sun produces all of the energy that we're going to receive that doesn't come from the Earth's interior. We don't get any real energy from intergalactic space, and the temperature distribution away from the sun as we take a look at the different planets. We're not looking at a scale diagram in terms of the distance of the planets from the sun, but it does show their size, and we can see the temperatures are listed down here in degrees Celsius, and the Earth sits right about here, right? So it's just over 15 degrees Celsius in terms of the temperature that we get from temperature that we're at given our distance from the sun. And then it gets considerably colder as we move out into the Jovian planets, where the average temperature in interstellar space is about minus 250 degrees Celsius, but we see those temperatures getting out lower and lower and lower and lower as we get away from the sun, and then getting higher and higher and higher as we go in towards with the terrestrial planets. And so what's coming off of the sun is a bunch of different stuff. We get the solar winds, which are charged particles coming off of the sun, interacting with our atmosphere, being deflected by our electromagnetic field. But then we also have a range of wavelengths ranging from ultraviolet light, possibly even X-rays, really, not possibly, but there are X-rays coming in off of the sun, and then all the way down to, low or long wavelength thermal energy, all of that, and including visible light, which is also a source of energy. If we take a look at the spectrum of radiation coming off of the sun, so we have incoming radiation at the top, and so we have radiation intensity coming in from the sun. And what do we see? We see that most of the incoming solar radiation is coming in as visible light. That's the big package of light. So we're talking about 400 to 700 nanometers in wavelength. And then we also get some that is what we call infrared or near infrared, and then we get ultraviolet. And that's the biggest amount of incoming solar radiation. And most of the ultraviolet light, you'll notice, is actually blocked out. And so it's blocked out because it gets absorbed by O3 molecules and O2 molecules, which break apart and then recombine to make more O3. So the ozone here in the stratosphere is doing the job of blocking out some of that really bad ultraviolet light. And so what ends up coming through then is lots of visible light, right, making it all the way through, and not really interacting with some of these gases very much, like CO2, H2O, okay, not affected very much. And so the total atmosphere is very good at blocking out a lot of stuff. You'll notice everything in black here, right, is stuff that is absorbable by these various chemicals. So O2 and O3, CO2, and then down here H2O. And we notice that the incoming radiation is not absorbed by O2 and O3, the stuff we want to see, which is visible light. CO2 doesn't absorb any of that. H2O doesn't absorb much of that at all. And so that most of that visible light and the ultraviolet and the ultraviolet light, the short wave ultraviolet light, and then some of that heat as well, makes it through to the Earth's crust. Okay? Where do these gases like CO2 and H2O come into play in terms of radiation? Well, they absorb long wavelength radiation. So wavelengths that are typically above about 700 nanometers or 0.6 microns. So everything on the right-hand side of this diagram over here gets absorbed by CO2 and H2O. And so how do we get all this long wave radiation? If most of the stuff that's coming in is visible light, is ultraviolet light, is short wave radiation, where does this long wave radiation come from? And it turns out that it comes from the crust. Okay, so UV light, visible light comes in and it hits the Earth's crust and it heats it up, right? It's energy. You can go outside and feel this. And as the crust cools down at night, what does it emit? It emits long wavelengths. So the crust emits long wavelength energy, and it's the short stuff here, the short wavelengths, that are coming in and making it into the atmosphere, through the atmosphere to the Earth's crust. Now, it's this long wavelength energy that then gets absorbed into CO2 and H2O molecules, and that retards its flow out of the system. So it works as a little warming blanket. The energy always has to leave Earth's system, but it doesn't do it quite as fast. Okay, as the radiation comes in, there's a number of possibilities for it. We've potentially could have reflection go on, and I'll talk about that. We haven't talked about it yet. What we've seen is absorption, or talked about absorption, so that's where the energy moves into a particular atom or into a particular molecule. Both this can happen in one of two ways. It could happen with sort of molecular vibration. Vibration occurs when the atom is vibrating, but it could also occur where we've got electrons jumping into different orbitals. So that's another source of absorption of energy, and then it has to be eventually lost from that system. So we've got reflection, where it just bounces off of objects or surfaces. It doesn't really transmit a lot of energy, but this surface right here will probably heat up locally. Okay, we have material that absorbs energy, and so eventually it has to re-emit it, out of the system. And then we have the possibility that the radiation is in the bottom right-hand corner, just transmitted out of the system. Okay, transmission means that it's not absorbed. Transmission means that there's no exchange of energy between the wavelengths coming in and the objects, such as molecular objects, gas objects, that make up our atmosphere. Okay, so the last thing we can talk about here in the realm of behavior is scattering, right? So here we're talking about one wave coming in, and it can be reflected, it can be absorbed, it can be transmitted as it just passes through something, doesn't interact with it. But here we also have to have scattering, where in the case of reflection, the wavelength comes in as one solid wave and exits with most of its energy as it's bounced off of a water molecule, right? So basically moisture in the atmosphere. Here it comes in, it hits the molecule, and then is sent off in all directions and slightly reduced. So the energy is split and redirected. So if we back up, we can have energy that's reflected, not much energy lost there, absorbed, transmitted, and then, of course, something that would be scattered and redirected. All those are processes operating in the lower atmosphere that we're interested in, and different features within the lower atmosphere, in particular the troposphere, will behave differently in terms of how they interact with light or UV radiation or infrared radiation. The term we want to kind of get in our head here is albedo. Albedo is the amount of reflected solar radiation that gets sent back out into space and doesn't interact with materials in that it doesn't really transfer any heat into the system. Okay, so even though the reflected surface, like right where you touch it, might have some heat in it, more or less when you have reflection go on, there's not a lot of interaction and storage or exchange of energy from wavelengths of visible light, let's say, into an object, which would then be stored as kinetic energy, infrared wavelengths, right? So when reflection happens, that doesn't happen. The storage of energy doesn't happen. It just gets sent back out into space. And different materials on Earth's surface, including man-made materials, will influence the Earth's albedo. So the degree of reflection is shown here on the left. So how much energy comes in and then is reflected out. So for snow, it's like 80 to 90% of the energy, total energy, gets kicked out, so it doesn't get converted. For clouds are good, but they have a weird kind of variable effect and that they're unpredictable. 50% of the energy that comes in gets reflected. Buildings, we're looking at 10 to 15%, and that is a function of how the building is constructed. And then things like forests, very low, grass, kind of low in the terms of reflection. So the total albedo for the Earth is the amount of solar radiation in various forms that enters the atmosphere and exits from the Earth's surface or near the surface without being absorbed. And that number you want to keep in your head here up on the right is 30%. Okay, 30% is reflected back out into space. Okay. The sources of reflected material, well, 5% come from the atmosphere, okay, 20% from clouds, and then 5% from land and sea. So even though, for instance, snow has an 80 to 90% reflectance in terms of the total energy it kicks out, it doesn't add up to very much in the total that's reflected from the land surface or from the sea surface. Clouds only reflect 50% of their energy, but they account for 20% of, essentially 20% of Earth's albedo. And the atmosphere itself is only 5%. So 20% of the Earth's albedo is tied up in clouds, and 10% is tied up in the atmosphere and the Earth's surface as reflective bodies. And the rest of it gets absorbed and reorganized to some degree. And sent back out into space, but only after, beyond there, only after it's converted from short wavelengths to long wavelengths. And so this is the heart of the greenhouse effect, is that we end up with short wavelengths coming in. These are UV light. This is visible light. Okay, it hits the Earth's crust and it heats the crust. It gets turned into infrared. And then is sent back out as infrared. Now, here's where the greenhouse effect comes into play. CO2, H2O, those gases or materials absorb infrared but don't absorb UV. So that basically means that the wavelengths of infrared, the long wavelengths, are something that can be absorbed by H2O and CO2. Other greenhouse gases would include the NOx, the SOx, actually, that's ammonia. Ammonia is not what I'm looking for. CH4. There we go. Yeah. So all those are potential greenhouse gases, and what what sort of distinguishes them from other gases in the atmosphere like O2, CH4, O2 or nitrogen is that there's at least 3 molecules in play, right? So, 3 atoms in play here. So the issue is that you have those atoms which have at least 3 molecules are capable of absorbing and vibrating. Those molecules will sort of have a vibrational energy, and that can be the same as the exiting long wavelength radiation. They can also absorb energy if it matches the energy of the electron shells surrounding some of those atoms as well. Anyway, so once that energy is absorbed into these various greenhouse gases, CO2, H2O, NOx, SOx, methane, okay, it then gets redirected. Some of it can come back to the Earth's surface, some of it heads back out into space, some of it's sent off in all directions. And the effect of this is to slow the emission of radiation from the Earth, right? It slows it down, means it stays hotter longer at the Earth's surface and in the troposphere. So this is a process that requires moisture, requires CO2, it requires these different gases, and these heavier gases are common and more abundant where the Earth's atmosphere is denser, and that's going to be also in the troposphere. Okay, all right. So that's one way in which the greenhouse gas or greenhouse effect will raise temperature. Now, it's the overall temperature of the Earth has very little to do with the greenhouse effect. That's a phenomenon that is sort of what we think is not necessarily new, but at least in terms of what human beings have done to the planet is relatively recent. But regardless of whether or not we have any atmosphere at all, the Earth's temperature is a function of the solar radiation that reaches us. And so it turns out that this is also going to vary with latitude, so that, at the North Pole it's colder than it is at the South Pole. And that has to do with the shape of the Earth. The Earth is round, and because it's round, we can look at how Earth's radiation is distributed across the globe. Each of these diagrams in front of you shows a different region. So we've got the equator on the left at A, and you'll notice that the sun's rays are entering or hitting the Earth's surface at 90 degrees. Okay? We've got mid-latitudes, so that's like where we live here in Chicago, mid-latitudes. We're headed up towards the North Pole, so that means that the sun's rays are coming in at a decreased angle. They're not 90 degrees. And so what happens is that the spacing here, as they've shown it, gets spread out. So we were at 1 width or 1 unit, doesn't matter. That could be a meter, it could be 100 kilometers. Okay, now we're at 1.4 units. The total radiation coming in is the same. So we're spreading the radiation over a larger length or a larger area, which means we're getting less radiation per length or less radiation per area. If we go to the poles, the angle decreases, right, to 30 degrees. And so now we've spread out the spacing here between the rays to 2 units, whatever those units might be. And so we're getting even less radiation per unit area. So if we look at the whole Earth and look at how that's distributed at the pole here, or at least and this is actually not at the pole. This is actually at the Arctic Circle. During a particular time of year, you're getting radiation that's coming in, and it's at 0, right? There's no angle, which means you're not really getting any radiation at all, much less per unit area. Where are you getting the most radiation? Where you're getting the most radiation per unit area, where the radiation intersects the Earth's surface at 90 degrees. And so in this case, at 23.5 degrees latitude, or say south latitude, you're getting radiation at intersecting the Earth's surface at 90 degrees. So that's the maximum solar intensity. And so as you head north, you get less radiation per area. And you'll notice it has kind of nothing to do really with the Earth's tilt. It has to do with the fact that the Earth is round. And that's one of the key observations here, that the Earth is round. Now, this is a particular situation that is a kind of season that's going on the Earth. And I want to talk a little bit about how the distribution of radiation, where you get less at the poles and more at the equator because of the angle at which the sun's rays intersect with the Earth's surface, is affected by this angle here, which is the tilt of the Earth. Okay? The Earth's seasons are not a function of its distance from the sun, and that's a key thing to remember. Do we get less radiation when we're farther from the sun? The answer is yes. Do we get more when we're closer to the sun? The answer is yes. However, it turns out that the coolest season in the northern hemisphere also happens at a time when we're closest to the sun, and the summer season happens when we're farthest from the sun. So really it has little to do with our distance from the sun and everything to do with the amount of time that we spend in the sun and the angle at which the sun's rays hit the Earth at our particular location. Okay? So those are the two key elements: the time that we spend and the angle. Okay? Got to keep those two variables in our mind. So where is the sun's radiation the most intense, and where is it the hottest? Well, it's going to be actually the hottest where the angle is the largest. So it's in the case here, it's at 90 degrees. And how much time are we spending in the sun? Well, that's a function of this thing, as what we call the circle of illumination. And so on the shaded portion of this diagram on the right-hand side, that's supposed to be nighttime, right? And so the Earth has a shadow, or the sun is shining from left to right in this case, and the right-hand side is in shadow because light isn't going to be bent around to illuminate the back side. And so as the Earth is rotating, we spend the longest days here along 23.5 degrees south latitude. So that means this position will be the hottest, right? And where do we get the least solar radiation? What latitude, just in general? Yeah, right. You can come up here, and this is going to be the lowest temperature. We're getting no solar radiation, actually. So we have the shortest days, or no daylight here at 66.5 degrees north latitude. And all of that is a function of the Earth's tilt. Okay? Now we take a look at this in the bigger picture. The image we just looked at is on the right here. This is called what we call the December solstice, right? It's the time when the northern hemisphere spends most of its time in shadow, or more time in shadow, and so it's going to be colder. And the southern hemisphere is going to be hotter because it spends less time in the shadow and more time in the sun. As we move into the equinox, the distribution of sun at the latitudes becomes equal, right? So even at 66 way up here and at the equator way down here, you're getting the same amount of daylight. You're getting 12 hours. Okay? But you're still not getting an equal distribution of solar radiation. You get less radiation up here, and you get more radiation at the equator. As we move into the June solstice, notice that the Earth's axis in the northern hemisphere is tilted towards the sun, which means that the northern hemisphere is going to spend more time in the sun than the southern hemisphere. So this is our summertime in the northern hemisphere, June 21 through June 20, or to roughly June 21 or June 22. And so we've got the December solstice, the March equinox, which we sometimes refer to as fall, okay, in terms of season. We've got the summer, and then we come back around towards the September equinox, or the vernal equinox, which is the autumn season, right? So this is the vernal equinox. Okay. And then back into winter. So what causes the seasons? It has nothing to do with the distribution or the distance from the sun. It has to do with the tilt of the earth, the amount of time, and the amount of time that we spend in the illuminated portion, or on the side of the circle of illumination that is illuminated. The longer time we spend in the sun, the more time we spend in the sun, the warmer the planet's going to be, or the warmer that you will be at that particular latitude. So this just breaks it down and gives you sort of a quantifies it, right? So during the June solstice, we're tilted towards the sun, and that means, so here's the circle of illumination right here. That means in the northern hemisphere, you can see right away we're spending more time in the sun. Everybody north of the equator up here, we're going from 12 to 13 to 15, and then if you're north of the 66.5 degrees north of the Arctic Circle, you're spending 24 hours in the sun, and everyone south of the equator down here all the way to the pole way down here is going to be spending less time in the sun. And so during the June solstice, we're going to have our summer season, and Australia, South America will be having their winter season. Reverse it. Here's the circle of illumination I'm drawing on here. Tilt the Earth away 23.5 degrees, and we get less or fewer hours in the northern hemisphere and more hours in light in the southern hemisphere. Okay? And so that creates our summer experience. Now, finally, here's our equinox. Just note it's the spring or the autumnal equinox. It doesn't matter. Okay? All of the latitudes, whether you're at the North Pole or not, all the way down to the equator, have equal time or equal length of day and equal length of night. Okay, so this table just summarizes all of that. So here's the summer solstice, winter solstice, and the equinoxes. So, at 0 degrees latitude during the summer solstice, you're having the length of day is 12 hours, right? If you go down to 90, so you're at the pole, you're at the equator here. You're at the pole down at the bottom here during the summer solstice. They're tilted away from the sun, and so that means 24 hours of darkness. Okay, and so the total number of hours then for each column should add up to what? Should add up to 24, right? 24 hours per day. So if you know the number of hours of nighttime, you know the number of hours daytime. It's got to just be subtracted from 24. All right, so to just sum up, we talked about how radiation, the kinds of radiation that make it into the lower parts of the atmosphere. We talked about how they're transmitted, absorbed, reflected, and how that contributes to the transmission of energy to the Earth's crust, which is essentially going to convert any energy that comes into infrared, if it already isn't as infrared energy, and send it back out, affecting greenhouse gases, which will transmit that energy back towards the Earth and sort of slow down the process of energy removal. And then finally, we talked about the distribution of solar radiation across the Earth's surface as a function of the shape of the Earth, or the angle between the incident rays and the Earth's surface. So that has to do with the fact that the rays are all parallel and the Earth's surface is curved, and as well as with the time during which we are exposed to the sun. So the longer the time, the warmer we get. And so that means that the seasons are a function of that time. We spend more time in the sun during the summer and less in the winter. And so this ultimately is connected to the time we spend in illumination is a function of the tilt of the Earth. So what causes the seasons? It is the tilt of the Earth. Next and last segment, we'll talk a little bit about the distribution of heat with respect to continents and with respect to the oceans, and how those distributions of heat and average temperatures and climate can be influenced